So I'm gonna start with the agenda. I'm gonna start off by defining machine learning, defining what supervised learning is. And then I'm not just gonna define what supervised learning is, we're gonna go into detail with the supervised learning algorithm, specifically linear regression. And the main idea is just to teach y'all what happens, how does it learn, quote unquote, and to demystify the magic or whatever that goes into it. And we'll do that. We'll go through the theory and a little bit of the derivations. We won't get too heavy on the math. If you know just basic calculus, you'll be fine, able to follow along. And then we'll just summarize. And, we'll do the code example. Like I mentioned, you won't have to download anything. You'll just have to follow the link and you'll be able to use Google Collaboratory, which I'll explain what that is later. So let's get started. So yes, so what is machine learning? I just pulled up this definition from the dictionary, and it's defined as the use and development of computer systems that can learn and adapt without following explicit instructions by using algorithms and statistical models to analyze and draw inferences from patterns and data. So I just thought I'd include that. Let me say what that means. Which is just that it's just algorithms that are being optimized to fulfill a specific task. And so that also leads to the discussion between what's the difference between artificial intelligence and machine learning. Artificial intelligence is a more futuristic general term, meaning that you're able to, for example, detect human feelings, but then also speak, or to be able to analyze something within a given context. Whereas with machine learning, it's a subset of artificial intelligence. It's very specific. If I train a neural network to only recognize cats, I can't feed it dogs and it won't recognize the dogs. And that's the difference between them, that with machine learning, it's effective, but it's also dependent of what you do with it. So if you train it on a poor data set, or if your data set does not represent what you actually want it to do, it's not going to work. And machine learning is the field of AI that has progressed the most. And it's at the point where you could make really efficient algorithms for very specific tasks. And I'll get to some of those in the next slide. And so this diagram that you see is just like the fundamental diagram that you see at the beginning of every machine learning textbook or book, and it just breaks it up. And so inside of machine learning, there's a field of deep learning, which we'll actually cover in here, and computer vision falls underneath it. And we'll go into that in the following weeks. And within machine learning as well, there's supervised learning, unsupervised learning, semi-supervised learning, and then reinforcement learning. And so all that term means is that it refers to how the algorithm learns. This is just math. This is just a function that is being optimized. And it's up to us to define that function and then for the optimization to occur. And so whenever we're speaking of the unsupervised or semi-supervised or supervised, we're just referring to how the function is being supervised, optimized. So in supervised learning, we have labels. So when we have a data set, we'll have an image of a cat, and then we'll have a label saying whether it's a cat or not. With unsupervised, there is no labels. You essentially just have a bunch of data that has no labels, and you're trying to make a correlation with it. In semi-supervised, there's a combination of both, where you have both labels and data that's not labeled. And so there's specific things you can do for that. And reinforcement learning, that's the one you've probably seen like being used to play video games. That's where it's had the most success. If you've ever seen a YouTube video where they make an AI learn how to play chess or play the game Hill Climb, I think I saw a video on that once. That's reinforcement learning. That's where you have to build an environment and make an agent that interacts with that environment and tries and experiments things out, and you have to define a reward. and based off that reward, it learns. So that's just a little introduction to a little bit of all of them. But for this workshop, we're gonna focus on supervised learning because it's the one that's progressed the most, and it's also the most beginner friendly. And the key is to teach all the fundamentals so y'all could branch out and do whatever you like, which leads to the next slide, why learn machine learning. You should learn it because you can apply it anywhere. Autonomous vehicles, medical imaging, aerospace, natural language processing, to predict stock markets. And those are just the ones that I could think of and that I knew specific examples of. The applications for it are endless. It depends on what you can think of. And another reason why it's worth and valuable to learn machine learning is that the ideas are very transferable. So for example, on the top right, I have a picture of lungs. And so a CT scans. And so a very popular network that's used a lot today came from that, UNet. And so what UNet does is basically it takes an image and then it converts, it kind of differentiates it. So if I have a picture of me, it'll make the background blue and then my face red and then my body purple. And so the idea is to get an image and to then break it up in pieces. And so that was used initially in medical imaging, but the idea was so powerful that people started using it in autonomous vehicles. So that's just one example of an idea being so powerful that you're able to transfer it over. And the example of aerospace is the recent NASA mission DART, where they sent a satellite with a huge camera directly at a meteor. And the idea was to change the orbit of it. And so for the last 4 hours of that flight, it was completely autonomous. And the way it did that was that the engineers just made sure that the camera was pointing at the 2 meteors, and then the system took over and it used object detection. And so here we have a little image of the big meteor, I forgot the names of them, and then the smaller one. And using computer vision and some controls process, it was able to hit the meteor and change the orbit. So, and this is just the beginning of it. It's starting to be incorporated into aerospace more and more, and just in every other field as well. So let's start talking about supervised learning. This course will specifically cover supervised learning. So as I mentioned earlier, for every data set, there's the data, and then there's a label corresponding to it. So here we have, let me see. Okay. So here we have a picture of a cat and then the label. Whenever we're coding or writing the algorithm, we'll have basically an X and a Y. And the X corresponds to the cat and Y corresponds to the label. And so that's how that's how our data set is structured in supervised learning. We're optimizing a function, which is called a cost function. And we'll go to that here today. And the way it basically works is that we get a data, we feed it through the network, and we get out a prediction Y hat. And this prediction Y hat is compared to the actual label Y. And so an analogy for it is think of you learning something, and the way you would learn to do it is by trying it, failing, and then making correct adjustments to get it correct. And so this is the same thing that's happening here. We have a network, which I'll label f of x, and that outputs y hat, which is a prediction. So we feed our data in here, we get y hat, and we compare y hat to y. So yeah, so that's supervised learning. That's basically it. Okay, so let's talk about how supervised learning, the training process for it. The first step for it is to do forward propagation. So what that means is that we get our data and we feed it to the network. Then we get our prediction y hat, and that's the forward prop aspect of it. that's just the beginning. In this workshop, we will actually implement both backward and forward propagation. So all of it from scratch. But once we start getting into deep neural networks, we won't be doing that because that's too much. It gets too complicated too fast. So we'll start using frameworks. But for this one, we'll just do it from scratch. And so then is the step of backward propagation, which is the arrows in red over here. So we have the cost function at the end, and it compares y. So we'll define it as loss equals, so the definition for it is, why did my color change? Okay. So it's, let me delete that. Okay, so we have a loss function, and it takes in y hat, and it takes in y. And so we'll leave it at that for now. But this is the function that gets optimized. The way that it learns is by minimizing the error. So we'll basically say, take in y hat, compare it to y, and then say how different it is. And then we'll do backward propagation. And so what backward propagation does is that it takes the partial derivative of the parameters that the network has. The network is made up of parameters W and B. And so what we do is that we get the error and we start to go back. And the reason why we go back is because we have to use chain rule. Because remember, all of these are calculations. So if we have X, we feed that into f of X, and that becomes y hat. Then we have loss, Ly, with y. And so these are just calculations that are taking place. And the way to get back to the beginning is by taking the partial derivative. And we'll talk about that. That's, I think the next slide. Oh, it's the one after this, or two after this. But so, as I mentioned before, linear regression is a supervised learning example that we'll look at. And I just want to emphasize, if you take one thing away from today, is that supervised learning training process is broken into two parts: the forward propagation and the backward propagation. In the backward propagation, we get the prediction, compare it to the actual, and say what's wrong about it, and then we update the network. And so that's just like the high level overview. I just wanted to start with that, and now we'll start to go into the specifics by looking at a specific example. Linear regression is what it's in the name. It's just, let's say we have a bunch of data, all of this here, and we're trying to find a relationship between it. This can be whatever. This could be the number of cookies sold, cookies, and then revenue. It doesn't matter. This only works for the linear relationship. And so the forward propagation, or the value of linear regression, is just this. Just a simple y hat equals W times X plus B. Now, I mentioned the parameters earlier, and these are the ones that I'm referring to. So the X gets multiplied by W and then added by B. B is the bias. You notice here, I want y'all to notice that for the general formula, I'm using an uppercase W because the W can be a matrix or a vector, depending on how big your data set is. Because let's go back to that previous example. Let's say we have a number of cookies, but then we also have another dimension extending out that says drinks sold, and so forth. And it could just become a higher dimension input. And so I just wanted to write the general formula with that. But for this workshop, we'll only be using a scalar value, meaning that it'll just be a number. And so if you notice, I use a lowercase w when using it. And so let's do the forward propagation. We're going to start by just working it out with the simple problem. And so we're going to have our data set pair here, X and 4. And so that's the data we have. And so, and W and B are both randomly initialized. For us, we'll just randomly initialize it to 0.5 and 0.5 here. And so, yeah, then it's just as simple as it looks. You just get 0.5 and you multiply it times 2, then you add 0.5 and you get a y hat of 1.5. And the actual function that we're trying to learn, if I remember correctly, is 2x. Yes, it's just that. So we're just trying to learn that. We're just trying to learn that by just looking at the data. So this is the network that we're trying to find, but we only have data to look at. And so the beautiful thing about machine learning is that we don't have to come up with this from ourselves. We just have to define the forward propagation, and through the algorithm that I'm about to show you, it'll reach this conclusion itself. So let's go to the backward propagation. So I've been speaking a lot about the cost function, and that's the function that gets optimized. And for linear regression, the cost function that we'll use is mean squared error, this one right here. So let's think about it this way. So earlier we got a prediction of 1.5. So let's come here and say y hat equals 1.5. And our actual data point, y is equal to 4. So I actually worked it out here. So we have x, y, that's our data. And we have a y hat, which we just got from our forward propagation. And then we just subtract 1.5 from 4 and we square it. Now, why do we square it? There's 3 reasons why we square it. The first reason is whenever the difference between the actual value and the predicted value are greater than 1, it's going to become a bigger number, meaning that the error is going to be high. So in this case, we have 1.5 minus 4, and that's wrong. It's very off. So we want to square the error, meaning that it's really bad. So we want to signify, hey, you need to adjust a lot. Whenever we have a value less than 1, let's say we had y hat equal, we'll call this y hat 1, and then we'll call this y hat 2. Whenever we have a y hat 2 equal to 3.5, we'll have, now j will be, and I'll call it j2, equals 3.5 minus 4 squared, and that's just 0.5 times 0.5, which becomes a smaller number, 0.025, I think. I don't know, I didn't use a calculator. But yeah, so in this case, so we started off with 1.5 and then we got to 3.5. We're getting closer to the actual answer. So we want our error to be less than whenever we're really off. And so that's the second reason why it's squared, because to account for when you're actually there versus when you're not. And the third reason why is the more complicated reason, but it's the reason that we want our cost function to be easy to differentiate. We want it to be easy to take the derivative of, because of this backward propagation, right? Because what we'll have is that we want to take a partial derivative, the gradient, to be able to adjust these parameters w, over here, this w. Because w and b are the 2 things that we need to learn, right? We need to learn that the relationship between the input data and the label is 2x. So that's the parameter that we need to adjust. So, okay. So let's go to it. So gradient descent, okay? So as I mentioned, we take the gradient, in this case, the partial derivative, since it's just a scalar value, dj dw and dj db. And so think of it this way. You have the error, but then you also want to find out why by how much that specific value, w, that specific parameter, affects the output. And so the visualization for it is if you have a slope. right? So for simplicity's sake, we're just gonna drop the bias, because if we have the bias in the b value, the b parameter, now our cost function is 3-dimensional. But here we want it to be 2-dimensional. So we'll do this. So we'll have J with respect to W. Actually, I'm getting ahead of myself. Let me explain one thing before. Okay. So we just want it with respect to W because W and B is what makes up the network. So we want to adjust the network. And so we find the derivatives with respect to W and with respect to B, and then we do what's called the update rule, which is where we get the current W and update it by subtracting lambda times the derivative. So you probably noticed the negative sign, or if you didn't notice it, then I'm gonna highlight it because it's very important, and I'll cover it in the next slide. But I also want to mention the parameter lambda. Lambda is called the learning rate. And so for this simple example, we don't have to worry a lot about tuning. And we'll actually cover how important lambda is when we get to the coding example. But lambda is something that you choose. So there's a difference between hyperparameter and then parameter. A parameter is the network versus a hyperparameter is the thing that you actually have to go in and choose and adjust and do with trial and error. And so, like I said before, we had the forward propagation with just the small parameter w, the lowercase w, to signify that it's just a scalar value times the input. So let's derive real quickly the derivative of the cost with respect to w. And so, like I said before, we're going to drop the bias to just make it simple, to only work in 2 dimensions. And yes, like Matt said, if there's any questions, please ask. If I'm going too fast or if I'm not clear, let me know. Yeah, okay, so let's just go. So let's start off by, so we want dj dw. So let's substitute this y hat equation into here. So let's rewrite that. So we have j equals wx minus y squared. And so now it's just as simple as it looks. Take the derivative on both sides. dw, and then on this side, dw. So then we have dj dw equals 2 times wx minus y, subtract the exponent, then times the derivative of inside. And remember, we're taking the derivative with respect to w. So then let me make that neater. And then that just becomes x. So I'll rewrite it for to make it look better. So then we have dx wx minus y. And so that's it. That's our value. That's the value that tells us, okay, you made a prediction, but it's off by this amount, and this parameter, this specific parameter is affecting the output by this much. And so then we'll use, this will give us a actual number. So this will be a scalar. And that scalar is the one we use over here to do the update. That's how the learning happens. That's how the network is optimized. So let's see. Yeah, so now let's talk about the negative sign. The negative sign is very important. So why do we have that there? So I'll start with blue to signify, so let's say we have, so remember, this is J, the y-axis is J, and the x-axis is W. So let's say we get an error. So we do our forward propagation and we get an error that lands right here. So we do what we did earlier, what we derived earlier, and we find the derivative right there. And so right here, we have a positive slope. And remember, we're trying to learn y equals 2x, right? So if you notice, the bottom of the curve is the actual value that we want to learn. And so this is where gradient descent comes into play. The analogy for it is a ball rolling down a hill. And so that's what the negative sign means. So here we have a positive slope, and we know our W in this case is, let's say, 2.5. So we know our W is larger than what we actually want it to be. So we get that positive slope and we subtract it over here to account for the fact that whenever we have a positive slope, it means that our W is too large. So then the W will adjust, and it'll become smaller to signify that, hey, you're overshooting, come back. When the derivative is negative, the opposite is true, right? Here we have, let's say, 1. Let's say our W is now 1. Here, the opposite is true. Our derivative is too small. I mean, our W is too small. So we have to make it bigger. And so that's why the negative is there. The two negatives will cancel out, and it'll make the W shift this way. And so that's where the analogy of the ball rolling down the hill comes from, where you'll start off just doing the forward propagation. You'll land somewhere here, and then you'll like adjust, and you might overshoot over here. Then you'll adjust again, and you'll overshoot there, and then like this and like that, until you finally reach convergence, when your algorithm learns the network that you want. It finds the relationship between the data and the label. Yeah, and so the ball rolling down the hill is the best analogy for it. It's the one that's most used. And this is done through the training loop, which will also go through in the code. And so just keep in mind, like, the most important thing I want to stress, it's forward propagation, forward, and then backward. So we make a prediction, we say why that prediction was wrong, we adjust the network, and we make another prediction. And we just keep looping and looping and looping until we make a convergence. And so one thing I want to say is that these networks get extremely large really fast. And these actual ideas have been existing, or have existed since like the 60s, some of them. So they've been around for decades, but it hasn't been until the modern day where we have a bunch of data thanks to our phones and the internet, and also the advancement of GPUs, that we could actually perform this. Because I mentioned that we have to keep making predictions and then making adjustments and then coming back. That gets really computationally expensive when your network is really large. And so that's just one thing I wanted to note, that supervised learning has advanced so much today just because of the computational power has increased. That's a question. Okay. Is the convergence always known? It depends. So it depends. So for example, let's say we had, let's go back to the case of, oh man, okay. Let's go back to this case here, right? So for this case, it's easy to know if the convergence is happening, right? Because we'll have, actually, no, it is, you will know it. In supervised learning, you will. I'm thinking of other types of learning, but for here, you will, right? Because eventually what will happen is that, let's call y hat 1, y hat 2, and y hat 3. So let's define those, okay? So, no, I think a better thing would be accuracy. Accuracy 1, accuracy 2, and then accuracy 3. So the way that you'll know whether your network is learning is if the error is going down, right? So here, was it here? Yeah, that was further forward. So here we saw our error go down from 6.25. It went down to 0.025. So that's the first step. That's the first step to know that your network is actually learning. That your loss, that your cost is going down. That means it's being optimized. The other way to know, which won't always be applicable, but it can be applicable for this specific case of a cat detector, is that your accuracy will increase. So as I mentioned before, you have a Y, but then you also will have a Y hat. It'll have a prediction. And so what you can do is you can find the accuracy, meaning that you'll feed it an image and you'll say, did it predict correctly whether it's a cat or not? And so let's say you have 1,000 images of a cat. And so let's say it detected that on the first try, so on the first training step of forward and backward propagation, let's say it detected about 15% of the time. Then it optimized and it went back. Now this time it's getting it 55% of the time right. And so then it'll slowly start to incrementally get up to 90 or whatever you want it to be. And so the point that you mentioned about convergence, that's really up to you to decide when to stop. Because you can get really specific with it. For example, they used to have coding competitions. I think they still do, for computer vision back in around 2011. I forgot the name of it, but it was basically just like all these universities would get together and just try to make the best computer vision application to detect cats, dogs, horses. And the accuracy back then used to be like 90, but they kept having the competition because they wanted to achieve 100%. So the convergence is up. So that's the two ways to know whether it's actually learning or not, to see, hey, is my error going down and is my accuracy improving? But then that's up to you to decide, because let's say you can get, let me go here. So let's say you can get 98.5% accuracy, right? So let's think of the specific, let's think about being an engineer doing this. Let's say you want to replace radiologist and automate that process, right? A radiologist with a team of radiologists, if they examine a CT scan, they're hardly ever going to make a mistake, especially if it's 10 doctors looking at something, right? And let's say you're trying to compete with that. And let's say the error rate of them is like 0, something like that, some made up number, but you have this accuracy. So to us, that may be correct, but then that means that 1.5% of people will be misdiagnosed. And so that's where you have to come in and come up with better strategies to convert this error down to 100%. So the convergence happens when you wanted to define it, I would say. It's kind of your metric. It's up to you. But the ways to know that your algorithm is actually learning, to see that it's actually going down this bowl, is by checking the loss to make sure that the loss is going down, then also to make sure that your accuracy is growing up. And then you decide what convergence is. You can be satisfied with an accuracy of 90, depending on, let's say you want to have an embedded system and you stress time versus accuracy. So you'd make a smaller network where it can output faster, but it won't be as accurate. Then that raises a safety concern, where if you have an autonomous vehicle that is accurate 95% of the time, then that means it might miss that one kid, like a kid, and then hit it, or whatever it may be. So that's why I really enjoy this, is that it's up to you, and a lot of it is up to you. Like, you have to define your metric, you have to define everything essentially. So yeah, so that's the question about convergence. So let's play out the little scenario of the ball rolling down. So let's play that out. So let's see. I'll use red. So as we had before, we had the x of y, the x equal to 2, and we had a y equal to 4. Then we had, remember, we randomly initialized the w to 0.5. and we do our forward propagation, and this time we get 1, right? Because 0.5 times 2. It's as simple as this look. Like, I just want to stress that, like, this isn't complicated. Like, it's just multiplication. Like, it's not that bad, or matrix multiplication. And so then you get your output 1, and you subtract 1 minus 4, and you get 9, right? Which is what we want. Our output, our prediction is really off from our actual value. So the error gets magnified. So let's plot that. So we had a 0.5, and then so it's somewhere around here. Oh yeah, this is 1, my bad. So it ends up like here, right? Then we use the equation that we derived earlier, the partial derivative, and we get minus 12, which matches what we need, which is here. Another cool thing to notice is that the further out we are from the actual value, the higher the derivative is, right? Because this is a x squared. So the right here, if you notice it, the higher the w, like the further you are from w itself, the bigger the derivative will be, which means that like you're really off. You got to adjust by a lot, which is another cool thing about it. And so yeah, so then here's our hyperparameter lambda, 0.1 and 0.1. So I won't get into too much detail about the hyperparameter lambda, the learning rate, because it's very complicated and it gets fairly complicated. But just know for now that generally whenever you're training a model, you want it to be between 0.1 and 0.1 to the 10, -5. So you want it somewhere around there, depending how big it is. And it gets really delicate. Yes?
Just move the chat.
Oh, okay.
This is blocked.
Okay. Yeah, I didn't notice that. Okay. But yeah, so we had a derivative of -12. And then we come down here and we just plug it into the update rule function. Yeah, to the update rule formula that I had later. So here we have W equals our initial value 0.5 minus 0.1 times -12. And there's that negative side canceling out, right? Because our value, though we want it to converge at 2, but our actual value is 0.5. So we need to adjust. We need to make it bigger. And so then we get a new value of 1.70. So then our network changes from being the network that we're learning changes from being 0.5 times x. Now it's y equals 1.7 times x, right? So it's starting to get much closer to what we actually want, which is y2x, right? So these are y hat, and then this is y. So this is what it actually is, and this is what we're trying to learn. Like that's that's one step of training. So let's do another step of training. And so we did a forward propagation and a backward propagation, and that's called a step. Now we're in step 2. We have our data set still the same, the new parameter, and we do the exact same thing we did before. Forward propagation here, we make our prediction 3.4, 3.4 minus 4, 0.36. Our error is going down. We know that we're learning. And let me plot that out. Where is that land on? 0.36, 1.4. So it ends up like right here. So remember, we were over here. Now we're all the way over here. So we took a big step really quick. This is a pretty simple network, so it doesn't take that many steps for it to learn. And so then we have the lambda, the hyperparameter stays the same. And then we do it again. We get W equals 1.7 minus 0.1 times the new loss, 0.36. And so then that becomes 1.94. And so then we're almost there. The actual value that we want to get to is 2. And we're already at 1.94 with just 2 training steps. So I'll leave it at that for then, because then you can see it'll keep playing out. Like it'll reach 2 eventually, depending how like they asked earlier. It'll converge, and it's up to us to decide. In the coding example that I did, I think I did 10 training steps where it loops around 10 times, but then it cuts off there. yeah, so so just to summarize one more time, we started off here, then we were here, and then we'll keep going, and then eventually get there. And so on a more complicated network, a larger one, it'll oscillate back and forth. It'll go here, then back, and back, and then back, but it'll converge. One cool thing I also didn't include here, but I just want to mention, is that remember how I mentioned the data could be multi-dimensional? So what happens is that you get this cost function with respect to so many parameters that you can't visualize it. So like, think of trying to visualize 8 dimensions. It's the same idea, like, but it still works. Even at the higher dimensions, it still works. So even if you have like a plane that has multiple pit holes, kind of, or like if it has multiple, I forgot what the mathematical term for it is, but like multiple peak, the opposite of a peak. I don't know. I can't think of it, but it'll still converge. So that's the cool thing about it. I don't know why I mentioned that, but I just thought that was cool. And so yeah, that's gradient descent summarized. Remember, forward propagation, backward propagation, and you repeat that until you converge, until you're satisfied, until you find the mapping from X to Y. I should probably write that. Let me see, or show that. Just show it real quick. So we have X and we have Y. We want to find a mapping from X to Y. So last thing before we get to our coding example. So far, we've only been dealing with one data point. I don't know if y'all noticed that, but I consistently used only 2 and only 4. That's not scalable. It's not. You cannot, let's say you have 1 million data points in your data set. You can't sit there with the for loop and loop through every single one of them one at a time. So we do, either you feed it the whole data at once, or you do batches of it, meaning that let's say it's like 1 million, and obviously you can't give it 1 million pictures at once. So you'll give it like 64 at a time, or 8, depending how big the network is. So I want to talk about vectorization. And so vectorization just means that you're not just dealing with one data point, but you're dealing with n amounts of data points at a time. And so the functions stay the same, all the ones that we covered earlier, but just this changes. So the cost function now is all the predictions. So the whole data set, all the predictions made with that data set, and then just the average of it, right? So it's like, so let's say like from here to here, this point there, then this point there, this point there, this point there, and just the average. So like, how off is the data set on average? And then the same thing for this and this. These are the derived formulas from earlier. I forgot about them for a sec. Yeah, we didn't derive this one. Just to save time, we won't derive it, but that's just, remember how linear regression is made up of the parameter X and B? We derived DJ, DW, but we didn't do DJ, DB, but it's just right here, right here. So yeah, so now let's start coding. Just click on the link, and I'll follow along on my computer so I can show y'all how it'll look. Okay. This one, share. Oh, can y'all see my screen? Okay, why am I trying to exit out of Zoom? Okay. So when y'all click on the link, y'all should see this page. Let me see. Y'all should see this page right here. Is this what everyone is seeing? It's the one on the PowerPoint. Wait, did we put the PowerPoint in the? Wait, oh, could you put the PowerPoint in the?
I'm putting the link on.
Oh, you put the link in there?
Yeah, I'm about to.
Okay. So can y'all see this page? Like, are y'all on this page?
Yeah, I just sent it.
Okay, you just put it in the chat. Okay. Okay. So once you make it here, just click on Open in Google Collab. I think you need, I'm pretty sure you need a Gmail account to access it. So yeah, I guess while people are doing that, I can start talking about what Google Collaboratory is. So just click on the link and they'll send you here. So I'm logged into my Gmail, so it's just here. So what Google Collaboratory is, it's just, I mentioned earlier that one of the reasons why machine learning has really taken off is because of computational power. And you need a good GPU to be able to run these complicated networks. So Google created a service where you can basically use a Google server and run a network on the internet without having access. Like if you don't have a powerful GPU, you can still run one on Google, on the Google server, Google Colab. And should I wait for people or y'all are good?
Yeah.
Okay. Okay. Is online good too?
Yes.
Okay. But yeah, so it's free, but they do put a limit onto how much you can use. So if you're training, like, I think that limit is like 5 hours per month, which is a ripoff. Like you can't do much with 5 hours, but if you really needed to, you could pay for it. But yeah, so let's get into it. So this is written in Python. If y'all know MATLAB, it's very similar to MATLAB. It's just a scripting language. And the reason why most machine learning frameworks are written in Python is that Python is very simple and understandable, and you don't want to add a hello.
Ready?
Hey. And you don't want to add something that's already complex in a complex language. So the idea is to just use something simple like Python, and yeah, just make it as easy as possible because it's already difficult to grasp. Wait, what? Can y'all see my screen? Okay, okay. Sorry.
The code?
Yeah. Okay. So yeah, so we'll be using two libraries from this for this code example. We'll use NumPy and Matplotlib. So you probably heard that Python is really slow, and it is, but people use it a lot, so they've developed a lot of frameworks in it. And NumPy is one of these frameworks that's used for scientific computing, and it's written in C++. So meaning that you get the luxury of working with Python, but you get the speed of using C++. And yeah, so the way you run the code is that you just click on the box and you click the little play button. Okay, I'm not trying, it's not a virus, so y'all are good. And then just click on it, and that's it. So then you run a code block. And so the way it is that instead of having one large file where you run all your code at once, you run it modularly, where you run it one block at a time. And so this is really neat for machine learning because let's say you can load in the data, you can do all these things, but you keep having an error at a specific point. So you just have that 1 point break and you don't have to run everything again and again and again. So yeah, let's do it. So first thing we're gonna do is create the data set, and it's just a simple data set. Remember, we're doing the y equals 2x. And so we make the x array here, 0, 1, 2, 3, 4, 5. And then the y array, just that times 2. And then we plot it. So this is very similar to plotting in MATLAB, if y'all know MATLAB from Intro to Programming. So same thing as before, just run the block. And we get this. This is our data set, right? So let's make it a little more realistic. Let's add noise to it. And so for the purpose of us all getting the same results, I initialize the seed to 1, which is just how random numbers are made. And then I get the X data, multiply it by 2, which is what we need, which is what we're trying to learn. Then I just added a random number to it, a random number between 0 and 1, which is just like it could be 0.25, it's whatever. It's like from a distribution. And then we plot it again. So now let's run this code block. And so now we have the same data as before, but now it's just different. It's not perfectly straight. And so that's just to kind of simulate how a real data set will look like, how you'll always have like outliers that are completely off, and you have to account for them. Okay. So yeah, so let's start with the first step, the easiest step, just forward propagation. And the way you do that is just this function here, W times B. Oh, my bad, W times X plus B. And what we're doing is we're defining a function that we'll use later in the training loop to do the forward propagation, to do the forward step. So once we have that, we just do run. So that's it. And so for those of you that noticed, we're multiplying a scalar value W with the vector, right? Because with an array, my bad. Because now X isn't just a single point, it's an array, like it's made up of 10 different points. So that's the nice thing about NumPy, is that it takes care of that for you. So it's just as simple as multiplying it by just like any regular multiplication. Next, we define the cost function. In this case, it's mean squared error. And yeah, so let's just do it. It's just following the function, 1 minus capital N. Then we multiply that by, so we're going to have to use built-in NumPy functions for this. The first one is np.sum. Then we want to take the square of the difference. So we do np.square and then y hat minus y. A little neater. And yeah, that's it. So first we square it. First thing, we have our prediction, the actual value. We find the difference between them, square it, and then we find the sum of it, and then we take the average of it. And so that's our loss. And like before, we just click the little cell block and run it. And so last thing we need to do is define the backward propagation. And so here I have written all the functions that we have. We have the partial derivative with respect to W. In this case, I forgot to make that a lowercase w since it's just a scalar value. Then the partial derivative with respect to B. And then we have our update functions. So here for the loss, we already defined the function for it, which is criterion. So I'm just going to copy and paste this, or actually I'll just write it out. So we have criterion N, and then we pass it y hat and y. So that's the first step. And the number of data points is found here with x.size. .size is just the NumPy function, built-in function that tells you how many data points you have. So we have that. Then we do the partial derivatives. So we have just as simple as following function. I mean the formulas: 2 divided by n times the same built-in function as before, np.sum. But then this time we don't have to square it. Oh, my bad. We have to multiply it by the x, right? It's right here. Let's not forget that. Oh, no, the x is inside. Okay. So it's x times y hat minus y. Just try to space it out and make it a little more readable. So yeah, so take the sum of it of x times y hat minus y, and then times 2 divided by n. Then we do the same for dB. 2 divided by n times the sum of just the difference. Like that. And then lastly, we update our parameters. So if you see the minus equals, that's just the Python short, like that's how you iterate or increment things with Python. If you know C++ or C, you know you do it like this. I don't know if MATLAB has a shortcut for it, but this right here is equivalent to saying minus. So I guess I'll just write it out this way. And remember, we pass in the learning rate, which is something that we control. And so we do learning rate times dw, which is what we have up here. Oh, and one last thing, to not have to write dj dw, I just wrote it as dw, just to not have to do that. Dw. Then I'll change this as well. Equals b minus the learning rate times dB. And so that's it. That's our backward propagation. And then we just, let me make sure everything's correct. Okay. Then we just run the cell block. Now we get to the training loop. This is where we define how many times we want that action of forward and backward propagation to occur. And so we don't, like, it's called a training step, but for some reason they call it epoch. I'm sure epoch stands for something that I don't know, but epoch is how they call it. So number of epochs means that, so if I said it's a 5, that means we're going to do forward and backward propagation 5 times. So there's going to be 5 training steps. And so first we randomly initialize W and B here. I define a list losses, and this is to keep track of the loss at every step. And then we start the loop. So we do for, oh yeah, I need to mention that. So this is how loops are in Python. So if you know C++, a loop is kind of defined as int for I equals 0 to I num epochs, and then I plus plus. I think it's the same for MATLAB. But in Python, you just do for epoch in range of 1 to number epochs plus 1. So that's going to make it loop 5 times. And so the first thing we did before I trained it was we just plot out the line. So we plot out the prediction that if the first line, and the idea is that for every training step, we get to see how the line starts to creep up on the actual data and how it starts to actually learn it. And so, yeah, so now we already defined our forward and backward propagation. It's just as simple as calling them. So all we have to do is scroll back up and see up to forward, and we pass it X, W, and B. So then we come down and we write forward, X, W, and B. And then we have backward propagation, which is here, and we pass it X, Y hat, WB, and learning rate. I don't want to write all that, or I'll just type it out so I don't go too fast. Backward, X. Oh, it's actually telling us what we have to do. Okay, so Y hat, and then Y, and then W, B, and then lastly the learning rate.
You have a question.
Oh yes.
Why do you need the +1 in front of the known epochs?
That's for plotting reasons. So let me show you. Why is it bugging? Oh, genius. Okay. So the reason why I do the +1 is that in Python, whenever you're looping through a number, if I do num epochs, if I do this, it'll do this. It'll make the epoch equal to 0, then 1, then 2, then 3, and then 4, then 5. No, just 4, right? But since I'm plotting the progress of it and I want it to actually be the correct number, I do from 1 to num plus epochs. So whenever we're looping through it, instead of it being this, it's actually 1, 2, 3, 4, 5. So that's just why I do that. So to account for, like, remember, like whenever you're looping through a for loop, you want to index like by 0. So the indexing starts at 0, but we're not trying to index a vector or something. So I just did that. So whenever we're plotting, it's not saying epoch 0, it's saying epoch 1. So that's why I did that. So let's get rid of that. And yeah, now we're done. We're done. Did I spell that wrong? Nope. Okay. And so then we just run the training loop. And then the last step is to just pass it the data and define our learning rate. So, oh, and also one last thing. Remember how I defined that that empty list at the top? At the end of the backward propagation, we get the new parameters W and B. So the optimization is occurring. But then also I want to keep track of the loss to make sure that it's actually learning. And so I output the loss and then I append it to it, meaning that I'm just adding it to the list. And so once the training loop is done, it'll have a summary of the loss at every position. So now we just run the loop. Oh. Let me get this. And so this is how the learning happens. So first, whoa, that's a little weird. Okay. It learned really fast. Why did it learn so fast? Okay. But yeah, so the first step, it just, oh, I know why. Okay, that makes sense. Okay, so first it started off at random and it was actually pretty in line for some reason. But then it's, so that's the, wait, am I plotting it at the end? No, okay. So it learned faster than I thought it would. So this is the random prediction that it makes at first plot. And so these are this is our data versus the network that we're predicting. And then we tune it, we do a training step, and then starts to get closer. And then by epoch 3, it's already pretty much fitted. And it just stays there. Like it's already, the error is already really low. So it stays there. And yeah, so next we plot the loss with respect to time. And so that's what we have. We have, first it started off with the loss of 22, then around 6, and then it slowly started to increment to 0. And so yeah, that's it. Like, yes?
I have a zero in the aspect.
Huh?
Do we need to change anything in the aspect? Because I have an error with that.
Oh, you do?
Let me just bring it up.
Okay, yeah, sure.
You're saying I have an error in that.
Let me see. Is everyone getting this error? No?
They need to say it.
You're good. Here, let's do this. I'll work with you after class after this oh, I'm sorry, I dropped your thing. But yeah, so if anyone else got that, no one else got that error? People online, no one else got it?
All good.
Okay. And so yeah, and so that's the demystifying thing. Like that's it. That's basically it. One last thing I wanted to touch upon, just to show you like that it's not as simple as it seems, is that let's change this learning rate. So I mentioned how it's very important to try to, whenever you're developing an algorithm, that to you, like there's no other way to do it but off of trial and error. And so I want to illustrate that in this simple example by changing the learning rate from 0.1 to 10. So does anyone have any predictions as to what will happen if I make it 10? It'll explode. Yes, actually, you're 100% right. Yeah. So let's run it. Let's run it with 10. So that's what happens. Exactly what he said. So first we start out here, but then we overshoot the data by a lot. Then we undershoot it by a lot. Then we overshoot it by a lot. Then we undershoot it by a lot.
Your second half.
Yes. And let's think about why that happens. So, right. So we have the error with respect to the parameter. And so remember how we had from the slides, we had a -12. So in the first or second step. And so what's happening is that keep in mind that W is a really small number. And so if our lambda, our learning rate is 10 and our loss is 120, I mean, no, my bad. If our parameter is 10 and our loss is -12 and our W is 0.5, we're going to be adding 120 to it. So it's going to go from being a 0.5 to now being 120.5. So now that's why we get this big difference, because this is without any training. Then we overshoot it by a lot because it's just adjusting it too much by looking at this equation here. So now let's do the opposite. Let's make this a really small number. Let's do that. So does anyone want to predict what this is going to do now? No predictions? It won't fix it. It will, but it'll take forever. So let's get to it. So it starts off here. Then it does this, and it does this, and it does that, and it never really moves. And the reason why it really never moves is that, let's go back to this update rule. Now let's say let's keep it the same as before. We have our partial derivative and we have -12. But then we're multiplying -12 by 0.00001. So that becomes a really small number. So whenever we're subtracting 0.5 or adding, 0.5 plus this really small number, we're barely, if not at all, moving the parameter. And so that's where that tuning comes in. That's where that trial and error comes in, where you have to constantly try to make it converge, make the accuracy grow up, make the loss go down, but you don't know exactly how to do it. And so I just wanted to illustrate that, just how in this specific case, the learning rate doesn't really matter. Like if we did a 1, I think it could converge. I think. Nope. Oh, it's still too large. Okay. But if I do what? 0.1? That's what we had before. Yeah, we had 0.1. Yeah, let's do 0.11 or 0.01. Let's do that. Even with the smaller one, it still does it. So yeah, so I just wanted to like give a little glimpse of that, just because once you get into a really deep network, you can get stuck on something for weeks, just trying to figure out what's wrong. And it could be just the learning rate is too large or too small. So it's, yeah.
We need to figure out the learning rate
By
by hand.
hand? No, there's an approach to do it. So since the learning rate can be very sensitive, you don't want to do it like, you don't want to, what's the word? You don't want to just, so if you have a really deep network, right, that takes, so let's say you have a network that takes 3 days to see whether it's correct or not. You don't want to sit there and just guess a value, let 3 days go by and be like, oh damn, nothing's happening. And then you have to come back and do it again. And you just keep stuck in this loop where you have to wait 3 days to see if it's actually working or not, then adjust it. So there's an approach where you do, you use that range I mentioned, 0.1 to 0.0 to the 5 zeros to the 1. And you plot it on the, and you plot like a log curve. I don't know if you've ever seen a log curve. And you go off the log because you don't want to change it too subtly, but too much at a time. So by plotting it on the log, you can actually incrementally see, hey, it's starting to converge here versus it's not doing it too much. But it's honestly just, you have to get a sense for it. And also, one important thing that you need to do if you're going to go into machine learning is that you constantly have to be reading research papers. Like I mentioned before, a lot of the ideas are very powerful and transferable. And why do something from scratch when someone already came up with a solution that may work for you? So when trying to pick a learning rate, I would say research to see if someone has done a similar problem to yours and see what learning rate they did, what parameters they had, and go off of that, and then use a logarithmic scale to then start to scale it up or scale it down. But yeah, yeah. So and this is just one part of the tuning, because then you also have to decide what network to do, and we'll discuss that in later weeks. And yeah, so now we can just wrap it up with the slides. How do I get them quickly here? Okay. Let me just get to them quickly, and we can wrap up. Here. Oh, damn it. I have it in my drive.
So many folders.
Yeah, hold up. Okay, so let's just wrap it up. Can y'all still see my screen?
Yes.
Okay, so yeah, let's do the summary. It's not gonna start from there. Damn it. Okay. Transitions, slideshow from current slide. Okay, so yeah, so just a quick summary of what we did. We defined machine learning, went a little into the details of the differences between the different types of machine learning, supervised, unsupervised, reinforcement, and semi-supervised. We examined supervised learning at a high level overview. Then we went deeply into the idea by examining linear regression. And lastly, we finished off with the coding example. So just a quick what's next type thing. Yeah, so I hope that y'all enjoyed this. I'm really passionate about machine learning. And I just wanted to give y'all like a to-do list, or at least a pathway to take if you want to continue learning about it. First, we will continue to host workshops for it. We'll go over multiple neurons on the next week. We'll go into deep learning in PyTorch, computer vision, network tuning, and then transfer learning, and finally the app that I spoke about. And so I don't want to scare y'all away with the math, because once we start using PyTorch, you don't need to do any math. Like, you just get the network and you define the forward pass, and the framework handles the backward pass for you. So you don't have to sit there and calculate 50 derivatives to get something done. So that I want to stress that, and yeah, like just go from there. And also a book that I recommend anyone that wants to get into machine learning to read is the 100-page machine learning book. It's a great book. It's only 100 pages, and it briefly covers everything with not too much math, but just the right amount. And lastly, I just want to recommend Andrew Ng. If you haven't heard of him, he's a professor from Stanford who has been doing free online, or not free online, but machine learning courses since 2010. He founded Coursera, and I think he's also founding an autonomous an autonomous vehicle company. And he's a very passionate person who just makes great content. The way I structured the course and the future ones are based off of his. And lastly, I want to point y'all to Free Code Camp as well. They also have a bunch of machine learning tutorials and tutorials in general if you want to learn how to code. Those are resources that I've used myself. And yeah, and also, as y'all saw earlier, y'all opened the code from GitHub. If y'all don't know what GitHub is, it's just a version control. I recommend that y'all start to learn it. It's used, if you're gonna work in software, you're gonna use it at any job. Like, it's very important. I won't go into the reasons why it's very important, but it's very important to know. And I would say just watch like an hour-long tutorial online, and it'll help you a lot. And so you can access all of our code from there, and I'll also post the key there, the key to the code. So if it didn't work for you, or if you wanted to look at it later, you can look at that there. And lastly, you can see all the other workshops that we have there. I pinned them so that you can see not only this one, but all the other ones. And so, yeah, that's it. So thanks for coming out. Hope to see y'all next week, and hope y'all enjoyed it.